I'm Aaron Muir. This is Ondrej Certik. We have Amit Kumar. I don't think Jason Moore is here right now. Sartaj Singh and Harsh Gupta. And this is a SymPy tutorial. If any of you are missing or don't have the materials, you can go to this website. It's also written up here. I guess that's the GitHub version, and that'll give you all your information. Okay, so before we start, we just want to go over a little bit of SymPy to tell you about what basically about the project. So what is SymPy? SymPy is a symbolic manipulation library, and our goal is to basically be the symbolic manipulation library for Python, for the SciPy stack. So it's completely open source, completely pure Python computer algebra system, and the goal is to be as easy to use and extensible as possible. And so if you've ever used any other computer algebra systems like Maple Mathematica or maybe some open source ones like Sage or Axiom, you may be wondering why bother rewriting all of that. But the nice thing about SymPy is it's completely standalone. So unlike something like Sage, which requires a large installation, SymPy is just a Python library. But it's completely full featured. So all the features that you would expect from something like that. It's BSD license. It embraces Python. So all of the everything you do in SymPy is just Python. So if you know how to use Python, you already know how to use SymPy in some sense. And we like for it to be usable as a library. So you can just import SymPy from your other code and use it that way. We've got a ton of features. This is more just to show off than anything here. But I think near the end, if there's any features that you want to know more about specifically, we'll open it up. And if there's something we haven't covered that you want to know about, we'll be happy to discuss. So the history of the project: in 2006, Ondrej started it. I believe he was a PhD student in physics. I don't know if you want to say anything more about.
Yeah, so my name is Ondrej. I was actually an undergrad when I started SymPy. I just wanted to have a library in Python that can do what Mathematica does. And I started small, and fortunately, later on, I was joined by many people.
Yeah, and so one of the big things that has helped SymPy over the years is Google Summer of Code. If some of you aren't aware, Google has a yearly program in the summer where they pay college students to write code for open source projects. And we've participated in that since 2007. And that's really helped our development because it's a really good way for us to get various things implemented in SymPy, and it's also really expanded the community. In 2011, Aaron, that's me, I took over as lead developer. So at this point in time, we've had over 450 contributors, over 400 lines of code, and SymPy is very much a real usable library. And we just, in the past year or past few months, we released SymPy version 1.0, which sort of signifies to us that SymPy is now a very real, stable thing that people can use. So I mentioned Google Summer Code. These are our projects that we have this year. If anyone's interested, these are the things that you should be expecting to improve within the next, by the end of the summer. We have a project on group theory and I'm sorry, I'm probably going to butcher most of these names, by Gaurav Dhingra. We have two projects regarding solve set, which we'll go over as the way that is our new function for solving equations by, I don't know how to say, Shitish? Shitish. Okay, that's good to know. So the K is silent, basically? Okay. And then another one by Shekhar Rajak. We have a project for holonomic functions, which, if you don't know what holonomic functions are, this is basically going to help us improve things like our symbolic integrator. It's a very general way of representing a large class of functions, basically as a differential equation. We have a project on, and another project on singularity functions for solving beam bending problems, if you know what that is. And those are by Shubham Tibra and Sampad Saha. And we also, there are a couple of Google Summer Code projects for SymEngine, which we're going to go over briefly here. SymEngine is a separate project that's branched off of SymPy to basically rewrite a core symbolic engine in C++ to be very fast. And there is a project to improve the polynomial functionality and to implement finite fields and set stuff by Srejan Garg and Nishant Nikhil. So our future plans, there's a new assumption system that we're working on. I believe we're mainly going to go over the older one today. As always, we want to make things faster. Ondrej is going to tell you a little bit more about SymEngine because that's his project. And we always want to implement more algorithms, more things so that we can basically compute more things with it. There's an older function called solve, and we're trying to replace that with a newer one called solve set, which is the same thing except it has a much cleaner API, and we'll learn more about that later. And we always want more people to use SymPy. And if you're interested in the full list of things we want, we keep all of our ideas on our Google Summer of Code ideas list, which you don't have to be a Google Summer Code student to contribute to SymPy.
Thank you. I'll take it from here. So I'll just say a few words about SymEngine. So SymEngine is a C++ library that it's pure C++, and then we have wrappers to various languages, including Python. And then now we are integrating it into SymPy. And the goal is to have the fastest symbolic library. The C++, it should be as fast as any other commercial or open source symbolic manipulation library. So we have a few slides about various projects that use SymPy to give you an idea how SymPy is used out there. So Sage is a computer algebra system, and it's a sort of like a distribution. It has dozens, probably hundreds of all kinds of open source libraries, including SymPy, and then it's able to, when you, let's say, want to integrate a function, you can choose if you want to use SymPy or Maxima or other codes. Sage Math Cloud is it's a web service which is able to host Sage, and you can create an account, log in there, and even use a terminal. And it uses SymPy as well as one of many other projects. MathPix is a really cool app for now, just for iPhones, which you can write handwritten math, and then you can snap a picture, and it's using some machine learning, I believe, to get a LaTeX representation of that handwritten math. And then they contributed to SymPy a module which takes the LaTeX to convert it to a SymPy expression, and then it's using a SymPy Gamma tool, which is kind of an online app, which you give it an expression. In this case, LaTeX, it converts to SymPy, and then it gives you all kinds of things about that expression, like derivatives, series, integrals, plots. So sort of like Wolfram Alpha. So that's really cool. But I cannot use it because I don't have an iPhone. But I've seen it at Aaron's iPhone. It's very impressive. PyDie. So there's a tutorial, I believe, either now or the next one. It's a multi-body dynamics. So imagine having some connected bodies like pendulum or double pendulum, or way more complicated, all kinds of robots, and it's essentially using SymPy to figure out the equations of motions. At the end of the tutorial, I'll actually have a notebook about this so that you can see it in action a little bit. IK-fast is a similar tool like PyDie, but just by other group. It also uses SymPy. And then SymPy has all kinds of wrappers, so it can be used in Octave as a module. It could be used in Julia using a SymPy, using Python Julia bridge. And then it's used in Mathix, which is another computer algebra system. SciPy is a library which it's a finite element library for solving PDEs, partial differential equations. It's using SymPy to derive some, I believe, some basis functions. And then there are some smaller libraries or sometimes modules. For example, the statistical modeling module is able to derive statistical formulas symbolically. So we have a few slides about all the authors of SymPy, all 450. And then if you are interested, we have a few talks. So there is a tutorial in the afternoon about PyDie. Then Aaron has a talk on Thursday, and I have about code generation. And I have a talk on Friday about SymEngine. And so now we'll start with Amit, and we'll start with the first notebook. And we'll switch our computers, hopefully it works.
So I'll be starting with the symbols and derivatives and basics of SymPy. So I assume that you have never used SymPy, and I'll help you getting started with SymPy. So starting SymPy. So math has a sqrt function which gives you the square root of a number. So I've called that function sqrt, math.sqrt. So you got the numeric result, 1.414. So this is actually not the exact square root of 2. Because if you add million digits after this, so this is basically, okay. So if you improve this, there can be million digits after this, the 7, but still it would not be the exact square root of 2. All right. So this is what the difference between numeric and symbolic. So let's call this sqrt function from SymPy. So you get this nice symbolic expression, and this is SymPy, and this is symbolic. So this cos function is from SymPy. So here is a small exercise for you that use the function acos and find the acos of -1. All right. So this gives you pi. Okay, all right. So this gives you pi actually. So, and you're supposed to call this function in NumPy as well as the default maths. Okay, so they use arccos, I guess. Yeah. And same happens for the maths one. Math also uses the acos, I guess. Yeah. So like you have ND array in NumPy and data frame objects in pandas. So we have a similar thing called as symbols in SymPy. So basically symbols are SymPy objects. So if you want to define a variable, you will simply call symbols. So this is how we define our variable in SymPy. And now you can create a SymPy expression, x plus 1. So if you do not have defined the symbols, then it would have given you a name error here. So let's create some more expressions. So basically, it uses MathJax to give this nice LaTeX printing in browsers. Thanks to IPython guys. Sorry?
You got the answer for cost minus 1 as pi. Is that also simple?
Yeah. Can you please repeat the question? I didn't got you actually.
He's asking if that pi is symbolic.
Yeah, the pi is symbolic actually. It's basically defined in SymPy. So for example, let's say,
Okay, so you type pi or?
Yeah. That's right.
so this is defined in SymPy as pi. So it's a SymPy object basically. So here's a small exercise for you. So define a couple of symbols, mu and sigma, through using the symbols function. And create this expression in SymPy, the bell curve. So a small exercise for you. Just raise your hands when you're done. And if you're facing any issues. Done.
How do you reorder the expression the way it prints?
Basically, that is canonical. That is it tries to print canonically. So you cannot change actually that. So for example, if you print x plus y or print y plus x, it will print x plus y every time. So it's kind of, for example, in SymPy, the expressions are stored as expression trees. So manipulating expression trees, you need some kind of ordering. So that's why it stores as a canonical way and ordered way, and prints the same way.
Yeah, for example, I wasn't able to make the expression.
Yeah, exactly. It's a bit old, so it will not print exactly like this. So anyone has any issues with this? Oh, the minus should be coming here. All right.
Well, yeah, that's.
Yeah, thanks. Good to go? Does that looks like bell curve? No, you can't actually. You can't actually. So this is a canonical printing. So like I told you earlier that the SymPy expressions are stored as trees, so you need some kind of ordering in that. So do things efficiently. And the printing is based on that order only. Oh, I see.
So the printing is technically separate from the internal representation. So it is possible. SymPy has a whole printing system to go in and modify the way things are printing, but there's sort of a default way that it does it, and it's not like extremely easy to change it, but it is possible to do it. And we do always like to, if something like this would probably be better as a fraction. So we are always trying to improve that so that it looks like the default looks better. Yeah, so the question is if you just use regular IPython. That's right. Well, so first off, you should always run this init printing, even if you're in like the Qt console or regular IPython, because that's going to give you nice printing everywhere. Oh, by the way, the question was how do you get this like in regular IPython? So there's two things first off. So let me just assign this to a variable. Equals. Oh, I should put it at the end. So there's a function called LaTeX that you can use. This returns a string of the LaTeX representation. And then there's also another function that you can use in the notebook called preview. And this has various options where you can save. But I think by default it's going to pop up. Oh, by default it's not going to work because he doesn't have stuff installed. But this, if you look at the documentation for this preview, it'll take the LaTeX, the string form, run it through LaTeX, and you can save it to a file, to like a PNG file or whatever you want to do. But again, if you're just working interactively, you should just, if you run this init printing, that's gonna give you the best representation interactively. It does, although that's like the last fallback because it's not very good. If you have LaTeX installed, it'll use that instead, which is much better because Matplotlib's LaTeX render is actually kind of bad. Yeah, like if you have LaTeX installed on your computer, it'll use that. And in the notebook, it's just going to use MathJax, so it'll just work out of the box in the notebook. And then in the terminal, it'll use like these Unicode characters to create like this 2D pretty representation.
How do you render the exact symbol without doing it in IPython? Like, I want to do like print of A.
Yeah, you can do that. If you do print A, that'll give you like this. Yeah, that'll just print it like a string, or you can like
P-print.
Right. So pprint will give you like this Unicode pretty printing.
Is there a way to get the output like
Oh, like this. I mean, yeah. If you just do A, after you've run this init printing, I think otherwise you have to use like this IPython.display.latex and then pass it in this LaTeX string or something like that. If I don't remember the details on that, I can go look it up. But I'm going to let him continue.
What's the actual name of the LaTeX library? I'm just trying to find and install it, and LaTeX doesn't.
pound package for that. If you have Linux, you should just install like TechLive or something like that, or even on OS 10, and then on Windows it's like it's going to be pretty large too, so just a heads up.
So moving on to the derivatives. So derivatives is one of the most common thing you do with the mathematical expressions. So I'll show you how to do that. So here's an expression called x square, and we'll differentiate with respect to x. And then some more expressions. Yeah, if it is multivariate, then also you can differentiate it. So take the derivative of bell curve with respect to x. So we found the bell curve recently. Oh, yeah. So find the derivative of bell curve with respect to sigma. So you can find the double derivative by differentiating on the previous results. So this is the double derivative. And of course, you can see that there are a lot of common terms here. So you can simplify this as well. So there's a function called as simplify in SymPy, which you can use to simplify the result. So actually, it's already simplified, actually. Not exactly. 1 second. Yeah, more simplified version. So you got sine square x plus cos square x. So by default, it will not do any simplification. So simplification is minimized, and you need to explicitly tell SymPy to simplify it. So then it will tell you that sine square x plus cos square x is 1. Similarly, we can find the third derivative of bell curve. And simplify that as well. So there's one more function called as SymPy. So don't confuse it with simplify. It's SymPy. So simplifying things. So basically, it can convert strings into SymPy objects. So this is a caret is not actually used in Python or not in SymPy lightly. So a lot of people tend to use this caret. And if you want to convert this string into a SymPy object, you can simply pass it to simplify, and it will give you the SymPy object corresponding to it. Any questions?
So you can use the simplify routine to define variables too.
Define variables.
So you didn't define R and
Okay, so define variables. What you can do is you can simply pass a string as, for example, x. So let's say so in this way you can define a variable. Yeah, exactly. It does. Yeah, you shouldn't, but it can. So you'll check the type of x, it is symbols. All right. So questions? Okay. You forgot to define bell, but still you are able to differentiate it.
And yes, and then I jumped
Oh, that's kind of strange, actually.
differentiating it and gives me 1.
So did you run all these cells before that?
I think that, yeah, that's, I think this is a quirk of the way Python works. Because the first
But
argument,
if I said zzz dot if it gives zzz is not defined, so how does it know what is bell and what is?
Oh, well, I'm sure that you've run this import star. You must have.
Yes, I did that.
Okay, so that's where bell is coming from. This import star is importing all the SymPy.
So
Function.
it has a bell.
Yeah, bell is the yeah.
I don't think bell is defined in SymPy.
Bell is like these
Oh, I see.
oh. Oh, well, okay, yeah, bell is defined as this thing. But if I do from SymPy, so this is actually one of the reasons why you should avoid import star unless you're really just working interactively, because SymPy has a lot of built-in stuff, and there's probably, like, for everybody, just a ton of stuff like math that you've never heard of before. And so bell is actually these bell numbers and bell polynomials. So bell, but the thing that you saw is actually sort of a quirk, because bell, if you look at the type of bell, bell is actually a class. So when you're typing bell.diff x, diff is you're calling diff as like the method. So this x is actually like the self argument of bell, and diff lets you omit the arguments if there's only one. So this is actually the same thing as this, is what you're getting, is what you're typing. Yeah.
He got it 1.
Actually, I'm a little unsure. Why was it giving him? Well, actually, so I'm a little unsure how you got what you got then. I don't know, but it's incorrect anyway, because bell's a class, so you should create it with arguments first.
So we need to investigate your notebooks, actually.
Well, no, it works. I tried it. I just don't. My understanding of why it
Oh.
happens.
What makes different with Echo is the flower bell. I mean, in that cell where we equated bell to that expression, we flower elements and SymPy.
So now we're talking about gotchas. So things that can go wrong.
Oh, you're doing x stuff. Self is x, so it's just doing x stuff. The derivative of x is 1. If the bell has nothing to do with it because you're just calling it unbound.
So you define a Python variable like this. For example, a is equal to stuff, and this is how you define a Python variable. And I hope all of you know this. And you define a SymPy variable like this. But you can do something like this as well, and it would work. And though you are not supposed to do this, so it's always recommended to use one-on-one mapping with variable names and Python variable names and SymPy variable names, so that avoid the confusion. So I'm defining a SymPy expression here, a, and I'm putting x equal to 3. So what do you think a would be? A would still be x plus y plus 1. So how would you substitute x equal to 3 in a? Sorry? No, it won't. So what are you saying? Simplify the expression a. No, it won't actually. So if you want to substitute a variable into an expression, so you'll use subs, a function called as subs. So you'll do a dot subs. So what do you think a would be now? A is still x plus y plus 1. So as you can read from here that immutability, so all SymPy expressions are immutable. Oh yeah. Sorry?
If you have downloaded notebooks earlier, just update it. Just get good.
Oh, yeah, exactly. Yeah. Yeah. So if you still print a, then it will still be x plus y plus 1. So the point is that all SymPy expressions are immutable. So the next gotcha is equal sign. So I define a SymPy expression a is equal to x plus y 1 whole square, and then another expression and what do you think this will give? False. So the reason it is giving false is, so equal to checks if it's exactly equal or not. So it doesn't check the mathematical equality. It rather checks the structural equality. All right. So structurally, these two expressions are not equal because this is a division. The head of this tree is division. So there's a multiplication, and you have x plus 1 and x plus 1 here. And this is a plus object, the addition object. All right. So in SymPy, if you want to check if two objects are mathematically equal or not, so you will subtract each of them, and call simplify not. So this will give you 0, and it means A and B are equal. And if you want to represent some equations, then you can use the equi functions. And you can access the LHS and RHS. And SymPy has this solicit function which solves equations. You can pass this equi object inside it, and it will solve the equation. So a cos of 1 by 2, so it gives you pi by 2. So a cos, arc cos 1 by 2 is basically pi by 3, so it's giving you pi by 2. So do you know why? Yeah, exactly. So 1 by 2 is basically 0 in Python 2. So a cos 0 would be exactly pi by 2. In Python 3, you'll get this 0.5. And if you still want to call this a cos with 1 by 2, so you will still not get the symbolic result, though you are passing it into a symbolic function, SymPy. SymPy is symbolic function that is a cos. So the reason is it will not give you the symbolic result because the input is float. So if you're passing in float as an input, so it will think that you need a float result. So that's why. So if you want the symbolic result, so what you can do is s dot half is basically defined in SymPy as a half. Or you can do this. So capital S is basically a shorthand for simplify. Or you can define rationals as like this. And the Python also has a fraction object. So if you pass the fraction in SymPy's acos function or any function, so it will simplify it. So by simplify, it will convert into a SymPy object. So the equivalent of fraction in SymPy is rational. So it will automatically convert this fraction 1/2 into a SymPy object that is rational 1/2. So this half is basically the rational. So there's another gotcha here, logical operator. So this XOR, this is a lot of people write this as a square in mathematics. So this is not actually square, the caret symbol. So this is a logical operator. And in Python, it is also a logical operator. So SymPy doesn't try to manipulate what is default in Python. So SymPy tries to follow Python idioms whenever possible. So, and of course, you can convert into a SymPy object if you want a square. So by default, you can do this, x square. And if you want it to convert to the XOR, so basically, if you don't want to convert the XOR to power operator, so you can pass the argument as convert XOR is equal to false. So in that case, it will convert into a logical operator. All right. Questions? Yeah.
What was the difference between rational and fraction?
So fraction is a Python object and rational is a SymPy object. So now we have advanced gotchas. So now this is an exercise for you. So how we have divided the tutorial is we have divided the time into 4 quantums. So after every quantum, there's a 10-minute break, and you're supposed to solve the exercises, and you can take break. And after the 10-minute break, Aaron will be joining you to explain you integrals, how integrals work. So you have a 10-minute break right now.
Okay, so we're going to move on now. You're going to have to pardon me, my sloppiness with this foreign keyboard. The next topic is integrals, and so we're going to the basic syntax. There's basically 2 kinds of integrals. There's definite and indefinite integrals. So your basic definite integral, just like integral of x squared, is going to be x cubed over 3. And so there's a function integrate here. Oops. And basically, you just do integrate and then the function and then the variable. And that'll give you your answer. And just to note that SymPy doesn't add any kind of plus C or anything like that. So it's just assumed that you already know about that. And then for indefinite integrals, so for example, the integral of x squared from 0 to 3, instead of passing the variable, you pass a tuple, which is the variable, the lower limit, and then the upper limit. Okay, and then finally, we can do symbolic integrals. So if you do an integral, well, this one's probably, yeah. So if you do an integral like this one, I'm not sure why this one doesn't evaluate, but if you do an integral that it doesn't know how to do, you're just going to get an integral back. And you can also use the integral with an uppercase I to create an integral object. And so that, so for instance, this integral is always going to stay unevaluated even if it knows how to do it. And so in general, the unevaluated objects in SymPy have these uppercase letters, and then the functions that evaluate have the lowercase. And then if you want to evaluate this, there's a method called doIt that you can call on it, and that'll evaluate it. Okay, so now here's some exercises. SymPy actually has fairly powerful integration algorithms implemented. So if you want to try some more complicated integrals to see if it works or if it doesn't work, sometimes if you pass something that it can't do, it might hang on you. So if that happens, just interrupt the kernel. So I'll give you a few minutes to do these exercises, and then I'll walk through them. Okay, so just to quickly go over what may have been missed on the recording. The question was how to do an integral using infinity, and infinity is this OO object in SymPy. And then, so here's the integral of this function from x from negative infinity to infinity, and you can see we didn't divide by square root of pi here, so that we're getting that. Initially I did not set these symbols to be positive. And by default, SymPy assumes that all symbols are complex valued. And so sometimes this can result in some rather complicated expressions because SymPy doesn't want to, it wants to express everything in full generality. And so often if you know your symbols are real or positive, you can set the assumptions on them, and that'll make things come out a lot simpler.
Also in Mathematica you can do, when you simplify something, you can put all these conditions.
Yeah, so that's actually like the new assumption system that we're working on, but that's still a work in progress. So for now, basically, you just do it when you create the symbols. And I don't know if we have assumptions later that we're going to be going over, or okay. Well, I can go over it now. Yeah, so the basic thing with assumptions is, yeah, when you create a symbol, like say A, and you want A to be positive, then you just set A is positive equals true. And then now, for instance, if I do, yeah, you need to define it, set it to a variable. So by default, A, if I just do A here, and then I do something like square root of A squared, that's not going to simplify because like the square root of A squared doesn't simplify to anything in general for complex valued A. But then, so for instance, if I say that A is, this keyboard, if I say that A is real valued now, it knows that the square root of a real number squared is the absolute value. And then even more restrictive, if I say A is positive, it'll just give me A back. So usually generally you want to set something to either be real or positive to help SymPy simplify things because of this particular issue with things like square root of x squared. And then another way that the assumption system, you can use it is if you have some expression here and you want to know like assumptions about that expression, you can do this like is positive on it. And this is going to return either true, false, or none. And so, for example, if I do A minus 1. So this here is giving me none, because if I take a positive number and subtract 1, it might be positive or it might not be positive. So there's like this, none is like the unknown case or the undetermined case.
What would they use when they define a symbol? What would they set it positive
Equal
equal false?
false,
Yes, why would they use it?
if you don't want it to be positive. I mean, so there's actually a bunch of different assumptions that are there. The real and positive are sort of the more common ones, but there's also like integer, irrational, imaginary, non-negative, and there.
Simply if I set it rational equal false, does this mean that that symbol can never be rational?
It means that, it doesn't mean that, so the question is if you set rational equal false, what does that do? And the answer basically is that the assumption system has like this deductive properties where it'll, like if I do here b equals.
It's basically a no, right? Because it's just saying it doesn't have to be.
It's saying that it isn't, but it's not going to like restrict you. Like SymPy generally doesn't check like later on if you try to replace b with a like square root of 2, it's not going to like give an error. The assumptions are more there for like SymPy knowing when it can do something than when it can't do something. So generally that's why you want to like use the assumptions to restrict it so that it knows that it can simplify things like this sort of expression. But like I believe now, yeah, so like setting it equal to false maybe doesn't tell you anything, but if, I think if I check, I'm not sure if this, yeah, so it doesn't know if it's irrational because I think irrational means real. Yeah, so for example, you know, if I say that b is real but it's not rational, then it's able to figure out that it's irrational. And like so, I mean the other possibility is like if I say n is integer, and then I say sine of n times pi, why did that not evaluate? Shift enter. Did I use up my quota of executions here? Okay, I don't know what's going on there. It doesn't want to evaluate that. Okay. Yeah, so if I set, for example, it knows that sine of an integer times pi is 0. Whereas, if I just do sine of x times pi, it doesn't know anything about x, so it's just going to leave that alone. Okay. Are there any other questions? Otherwise, we're going to move on to this 5 notebook, which is numeric evaluation. So SymPy, there's a library called mpmath, which is a dependency of SymPy. mpmath is a pure Python numeric library that does arbitrary precision numerics. And so we're going to see here. The easiest way to sort of do this numeric evaluation is just to sort of substitute numbers in for your symbols. And if you do an exact number, it's going to give you an exact answer in general. So our cosine of -1 is going to be pi. And now if I want to know the numeric value of that, use this evalf method. And eval_f will take an expression and numerically evaluate all of the numerical things in the expression. And so, like I said, MP-Math, which is what SymPy is using under the hood here, has arbitrary precision numerics, which means that you can take any number of digits for any expression that you want. I think by default it uses 15, but for example, if I want 100 digits of pi, you can pass 100 in to eval_f, and that'll give you 100 digits of pi. Okay, so here's an exercise. So I perhaps didn't, maybe it wasn't clear, but subs, you pass in a dictionary of the thing you want to replace and the thing you want to replace it with. So let me just show you here for this exercise. So we want to replace n with 2, y with 0, and z with 3. And you can see this was unevaluated, so it's still going to be unevaluated. But now we can call do it on it, and it'll give us an answer.
What is do it if you a 9, but eval after you
Right. So do it is going to try to do. The question is, why does do it give 9 and eval_f gives 9.0? So let me just say. Oh, okay. So let me. Yes. How do I do this? So do it is always going to try to evaluate the thing symbolically, basically using the symbolic algorithms. Eval_f is going to do a numeric integration on this, and eval_f is generally going to give you a floating point number as a result. So these are actually calling different algorithms here. Do it is first evaluating this integral and then substituting in 3 and 0 at the endpoints. And eval_f is actually taking a numerical, some sort of numerical quadrature on this integral here, and it's getting the result of 9.0. Okay, so there's another exercise here. I'm just going to go ahead and do it. Okay, and so the exercise now is to take this one and use eval_f. So I could still do it, and that would give me this answer. But if we want to know a numeric solution, and like I said, this, because we're calling eval_f here on this integral object, this is actually doing a numerical integral. So this is actually, it's actually different if we do this eval_f directly on the integral versus if we first do it and get this answer with logs and then eval_f that. So let me copy. Copy. I mean, they're the same number, obviously, but these are calling different algorithms. So this one up here is basically evaluating this log 100 minus log 5. And this one here is taking this integral, this, taking this integral and evaluating it numerically. Any questions? Okay, so now we're going to get to a fairly important function for SymPy for many use cases, which is lambda-phi. So lambda-phi is basically the way that you convert a SymPy expression into a function that you can numerically evaluate with NumPy arrays. So it's takes its name from the Python lambda function. So the syntax is similar. First you have the variable, and then you have the expression. So here f is lambda-phi on the variable x with this expression x squared, and that's going to give you a function. And when you pass in some values to that function, like 3, that's going to give you 9. And so now we take the same thing, and we get a NumPy array, and we pass in that NumPy array, and it's basically going to evaluate our function on this NumPy array. So a very common use case for SymPy is to use it to symbolically derive whatever equations you're working with, and then once you've done that and you want to numerically evaluate them, you pass them into lambda-phi, and then you have a function that from the expression that you created that you can use with NumPy arrays. So here's an exercise. There's some physics function here that if you want to know more about, you'll have to ask Ondrej, because I don't know. But this RNL is the radial wave function for carbon atom. It says carbon. I don't know. If you do 3 and 1, does that... Oh, yeah, so it's carbon because we're setting R equal to 6 here. Anyway, this is the expression that we're evaluating. And so now the exercise is to create a NumPy function out of this expression using lambda-phi. Okay, and so it's not, the answer's pretty simple. We're just, it's just f equals lambda-phi of x, and then this expression, expr. And by default, it's going to use NumPy. So you can also pass in this NumPy as the third argument, but it's going to, I believe NumPy is the default. Lambda-phi also supports some other modules like numexpr. I think you can use npmath or the standard library math if you don't want to use NumPy. But for most people, NumPy is the preferred backend, so that's why it's the default. And so now that we have this NumPy function, we can use matplotlib to plot this function. So we create a lid space from 0 to 5, and only length. Oh, do we not have the latest version of SymPy on here? I was pretty sure NumPy was the default.
It is now.
Yeah?
Why would you not use NumPy?
Well, that's exactly. So maybe I might be thinking of something that never happened. This is actually, we're running the development version. Yeah, so that might be something that might be an issue that was actually not fixed yet. But so I think for now you should pass it NumPy. But yeah, it probably should become the default. Create a NumPy. So now the exercise is to take this expression and do the exact same thing that we just did, except with the derivative of the expression.
Is this happening in C script? C++ script?
Pardon?
Does this compute it on C++ script?
Lambdify. So Lambdify, basically Lambdify, what Lambdify is doing is, so NumPy, here's our expression. Here's our expression here, 8x over 3 times negative 4x plus 4 times exp negative 2x. So you can create this function with NumPy. So NumPy has like an exp function.
I understand what lambda does. I'm just asking, is it executing at C++ type like speed because of how we've done it?
It's going to be executing at the same speed that you would get if you created this function with NumPy. So I don't know if that
Yeah, I think NumPy was
right. So like one issue that you can have sometimes with NumPy is that if you have this large expression, every time it has to do this unboxing and boxing all the time. If you every time it passes in the array, so Lambdify is not going to be as fast as possible. We'll go over later in the code generation, hopefully, some ways that you can make it as fast as possible. For example, one really simple thing that you can do is take Numba. I don't know if you have Numba installed on this computer. You do? Okay. So let me just show you here. So let's see how fast it takes to evaluate on this NX array. So I don't know why it would be cached, but yeah, okay. So for example, if I take Numba, just take numba.jit of our lambdified function and use that instead, that's going to be a little bit faster. And the time difference will be more and more significant the more complicated this expression gets, because that's the more basically the more terms you have, the more NumPy has to do all this unboxing, which is what makes it inefficient. Pardon? Oh yeah, sorry. And there's also an example of this in the code generation notebook. So basically, to answer your question, each of these individual functions in the expression are going to be evaluated at fast speeds, but the entire expression could be slow because of the way NumPy works.
So it's number compatible. So right there it's compiling to LLV.
Yeah, when you use NumPy, yeah.
So only the NumPy is
Yeah, well, because basically these individual functions are all implemented very fast in NumPy. The only thing that's slow is taking each input, and it has to go down to C++ or it's probably Fortran and evaluate it, and then it has to take it back to a NumPy array, and then it has to, once it has the larger expression, it has to do that again. So for example, if I change this n to, like, say, some larger number, I get some bigger expression. Well, apparently it's not.
Not accurate for that.
What's not accurate?
Time it is not probably accurate to measure the speed of the function because it averages and it says the slowest run is 930.
Oh, that's, yeah, so basically
it
whenever you use time it on a numba.jitted, it's always going to say that, because the first time it runs, it's really slow because the JIT hasn't warmed up yet. That's just the way numba works. So numba is only effective if you're running a function many times, because that's the way that just-in-time compilers work.
But it also caches the result because we are evaluating the same function again, so it is probably.
Yeah, but I don't think Lambdify is caching by default, as far as I know. Oh, this should be a 3. This is probably already as fast as it can be, which is why we're not seeing enormous differences. But if you have some huge expression, there are definitely ways that you can be faster if that's a problem. So let's do this exercise. So here's a derivative of, of the expression f prime x, right, and so let's take this, copy, paste. I actually don't know how to plot these alongside. How do I plot two functions alongside each other with matplotlib?
It's plotted the same cell.
Oh, so I just do.
Yeah.
And I forgot to do this again. Right. So we can see here it looks like the green one now is the wave function and the blue one is the derivative. So this basically gives you an idea. This derivative might be something that you want to use SymPy to calculate, because you don't want to try to take the derivative by hand and mess it up. Or this might be some much larger expression, and then you need to evaluate that derivative. Okay, I think if there's no questions, we're going to move on to whatever's next.
Solvers. Hello. Now we'll be talking about solvers. So open the second notebook 02. So we have a function called solvset, which can solve equations symbolically, and it returns a set of the solution. So as usual, we init the SymPy and like do the symbols. Then like if you want to solve a basic quadratic equation like this, so I just do solvset, then the expression and the variable I'm solving it for. So one thing you should notice is we are importing solvset explicitly, because solve set. So it's not in the main namespace yet because it's not complete, but like still we recommend using solve set. So yeah, so try running this. Try solving for this equation and see what you get. We did? Uh-huh. Okay, so we did. So if you solve this, if you try to solve this, it's a null set. So why is that? Because this expression is false. So as in like, so as Amit has talked in the gotcha section, double equal to stands for Python equality, which is not really an equation. So if you want to solve something, you give the expression which should be equated to 0. And the variable you are solving it for. So one very new thing about solve set is it can also represent solutions which are infinite. So for example, if I'm trying to solve for sin x, so it gives the set 2n pi for any integers, union 2n pi plus pi for any integers. So it should be n pi for any integers but like we are still working on that so that we get the most simpler solution we can. So now if we try to solve if I try to solve exponent exp minus 1 in x, so we get the solution n 2n pi 2n I pi. So yeah, cool. Am I audible now? Great. Yeah, so when I'm solving exponential minus 1 equal to 0, so it gives 2n I pi for any integers. And why is that? Because exponential, because in SymPy, symbols are by default complex. So it solves the equation in the complex domain. So we have an argument in solve set which you can use to change the domain of the domain in which you are trying to find the solutions. So if I say domain equal to s dot reals, s stands for singular objects. So like s is a class which yeah. So if I say it's reals is a set and S stands for singleton. Yeah. So singleton is a collection of all the singleton objects we have, and so S dot reals is a real set. So if I try to solve exponential minus 1 in real domain, so it gives 0. That's it. Yeah. So we also have so solve set cannot solve every equation as you expect. So for example, if we try to solve this equation, e exponential plus cos x plus 1, so we don't have a symbolic solution for it. So what SymPy does, SymPy returns a condition set. Condition set is a set which represents equation which is not solved, or a condition which is not like for x for which all x in real which satisfy this condition. So it stands for an unevaluated object like you saw in integral. So this is the equation. This is the set of the solution which is not really explicit. So solve set aims to return all the solutions it can return. So one of the problems with earlier solve function was it never gave you guarantees if you're getting all the solutions or not. So what solve set does is it tries to return the solution it can try to find, and for the other things, it returns you a union for solve set. So in this equation, it can solve the x minus 1 part, so it returns 1. But for this part, it cannot solve, so it returns the condition set object. So when you're trying to use solve set, you don't have to have the equation in numericals or in numbers. The equation can be in symbols. So here we are defining 3 symbols: height, width, and area, and we can try to find out what's the height given area and width. So it gives area divided by width. Yeah. So here's an exercise for you. Try to find the radius of a sphere given the volume. By the way, any questions for solve set? Yeah. Why is it given this way? Yeah. Yeah. So we define like volume and radius as positive symbols, and just given the expression for the volume and plug it and solve it for radius. So you got the solution. So earlier you were saying like a lot of strange things that happens. So if I say positive, so it tries to put the condition. Yeah, so I have not defined radius as positive, so it tries to put the condition when the radius is positive. And like this is, so it says it should be in the real line, so that's why it takes an intersection with minus infinity to infinity. Yeah, so Aaron already talked. Yeah, any questions about solve set? Or we should probably do some more examples, I guess. So anyone want to try some equation which you want solve set to solve? It will give a yeah, it will just return some unvalidated condition. Yeah. No, it won't give not implemented, I guess.
Condition setting.
Yeah. Uh-huh. What's the equation again?
Zeta of x.
So zeta is probably defined, right? Of x equal. Anything else? Anyone want?
I'm missing the condition set section. Like the old calculator.
Yeah, probably you should pull it. Just pull the new changes in the repository. So you can try to substitute values in it with condition set. So it says false. Like, so you can use condition set to maybe try if some equation is satisfying or not. And like we are building more methods in it so that like you can simplify condition sets, or it can do intersection with other things and all. So yeah.
How do you specify that the solution is positive?
So if you want to specify if the solution is positive, you just put the domain as an interval minus infinity to infinity, and it will try to make sure the solution is positive. So it gives 1, and x it should be
You don't minus infinity to infinity.
yeah. Sorry. Yeah, so 1, and it makes sure the x is in the positive integers, positives, and the equation. So you can also put integers and all. So one new thing which is coming up is, so it doesn't do anything special now, but it, like what we are trying to do is connecting to Diophantine solvers. So we also have a Diophantine solving module. So when you give domain as integer, so it will like use a Diophantine solver to install set and gives you the solution. Now it doesn't use, like, we have a separate Diophantine module which is not connected to solve set yet. So this is one of the part of one of the GSOC project. So like in backend, when you give different domain, it sometimes uses different algorithms. So for real, it has different algorithms, and like for somewhat different algorithms, and for complex domain, it has different algorithms. And if like for integers, we'll try to use Diophantine. So this is a common API for everything. Earlier, the Diophantine it is supposed to be a common API for everything. So we have a different Diophantine solver, which like if you go 2 years back, so you have, if you want to solve Diophantine equation, you have to specifically call it Diophantine solver. If you if and like and solve it, there's no clear separation between the real solver and the complex solver. So solve set fix most of those things. Any more questions? No? Great.
If I get two solutions, how do I select one solution?
Mm-hmm.
How do I,
So if you have a finite set, say, this one,
how do we use these solutions to do computations?
say, say you have equation, yeah, the quadratic equation. So, so you can like convert it into a list and use the solution. If it is, say, it's infinite solution. So you don't give a list because it's an infinite generator, but you can like iterate over some elements of the list. So you can do sol dot iter. Hmm? Yeah. Hmm? Yeah. So you can create an iter item and iter object, and you can iterate over the solutions. So you can do it like whatever times you want to do it. As next, right? What? Okay.
Can I ask you, can you go to this exercise where we need to solve that for ages?
Yeah. Yeah, this one. Mm-hmm.
Can you remove or set positive equal to false?
Yeah.
And now, let's get one of the solutions. So how would I do that?
So, yeah, so it is kind of difficult. We can, because, so what it is print. So it's an intersection object, so then you have to get the second intersection, then, I mean, um, so this is the second element of the intersection, then you have to do. So this is a piecewise function. So, yeah. So this is the piecewise function you are getting. You can substitute things in this. So uh, yeah, yeah. Oh. So you can substitute the variables there. Yeah, but I understand that getting the solution and like using it computation is kind of difficult. We are working on that. So, yeah. So in the subsequent exercises, we have talked about like how you can use substituent with solve to get the equation. So yeah, Aaron already talked about substitution. So if you have some expression, you can substitute some value to it. So if I do x square subs with x with y, so it substitutes x with y. You can obviously have a numerical value in it. So x square substituted with 2 is 4. So try substituting sine x in x square plus 2x plus 1. So you simply do x squared plus 2x plus 1, write the equation, and then substitute. So quadratic equation in sine x. And you can use substitution as the solution you get from solve set. So we have solved the equation, got the like, solution item, then then we can define a parameter, and if we try to substitute the expression of height in the perimeter, we get this expression. So yeah. So now try to compute the surface area of a sphere in terms of volume. This should be possible. So yeah, so you define the expression for surface area. Which is 4 into pi into r square, and then substitute r with solution you got. So here is surface area in terms of volume. So SymPy also have a plotting module, so you can plot equations, like symbolic equations, and like you can use. So if you don't have matplotlib and all, so you can use text plot and like few other very low dependency things to plot the equations. Great. Any questions? So you people can take a 10-minute break, then.
After the advanced calculus slide.
वो skip करता है? Yeah. So we are kind of short on like, so you can take a like 10 minutes break, go around, drink something, and come back. So we'll continue after that.
It's very easy to get the series expansion of some expressions. Say you have a sin x as an expression. So we can just call the series function on it. And you get a series expansion. What series does is it's calculate a certain number of terms up to a certain order. We can change that as well. Say we want the first 10 terms, so we can do that. What doesn't do it? Oops. Oops. So this is a series extension of sin x about 0, and we get the first 10 terms. SymPy also allows you to compute some special series like the formal power series and the Fourier series. Formal power series is just like Taylor series, but without the convergence conditions, like if we replace it with a numeric number, then it has to converge. So it's just an infinite representation as a polynomial of any function. So it's very easy to compute using the formal power series function, FPS. So we get a series like this. So this is very similar to what series does. But there is an underlying difference in the how it's constructed. The formal power series, unlike series, will not just give you 10 terms. It will give you an infinite representation. And how is that done is by first computing a formula for the coefficients and then returning the results. So it's by the infinite attribute, we can see how the series is represented as a formula. So what advantage does this give is that you do not have to compute again, say, you wanted now the 50th term of the series expansion. You just computed the first 10 terms. So if you have computed a formal power series object, you can just do term 51 or exp underscore series 51. If you want a truncated series for performing some operations, it's very easy to do that as well by using the truncate method. So a little exercise, try computing the formal power series of log 1 plus x and try to see how is the infinite representation represented. So here are the solutions for the above exercise. Any questions so far? Oh. Okay then, let's move to Fourier series. Consider us, yes?
You can't are you allowed to use the substitute?
Yeah, you are allowed to use that, but in general, mathematical definition of form power series, it doesn't guarantee the convergence conditions. In this case, it will converge. As you can see, this is just similar to a Taylor expansion of log series and exp series, but for other functions, form power series will not do that. It's just an infinite representation as a polynomial. So that's the mathematical definition, but subs and everything will work here. So for just an example. So that works. Fourier series can be computed using the Fourier underscore series function. So this is the definition for a sawtooth wave. It is periodical, as you can see that. So we can just simply compute the Fourier series. Here's how it looks like on a plot. This is done using SymPy's plot function. If you want to study upon why it behaves in this manner at the discontinuities, you can go to this link as well. This also computes an explicit formula rather than giving just a truncated series, say for the first 10 terms or the first 5 terms. So you can index in constant time. So there is no issue. You can do 51, you can do 100. So as many terms as you want. Sometimes in Fourier series analysis, we need to shift the series or scale the series. Rather than recomputing the Fourier series, we can easily do that using the shift and the scale function. So this shifts by 10 and this scales by 10. Let's do a small, yes.
You tried the truncate example on the sawtooth series with 1,000.
Truncate example on 1,000. Okay. That should work. Oh. Actually, what this will do is it will generate an add object, SymPy's add object. So maybe we are not able to handle these many terms. Maybe.
Yeah, so SymPy, because the expressions are these trees, a lot of the algorithms are recursively, so sometimes you'll get these conversion issues.
Oh. This works for me.
Well, I think this computer has a development version, so
That's,
maybe.
Okay.
Maybe.
Is there a way to override that? So it's-
Yeah, you can up the stack limit. There's a limit to how much you can do that before something crashes. But yeah, there's like sys.set
I don't know how many terms on these.
stack size or something like that.
So the full 1,000
But
terms.
you can also like you open an issue, just like rewrite the algorithm so it's not recursive.
Just a small exercise now. Here's the definition of a square wave. Can you all try to compute the Fourier series of this? You will need to use the piecewise function to define this. I don't think so. So maybe I will tell. So sometimes functions behave differently in different intervals. For that, we can use piecewise. They have an extra bracket here. Oops. Oh, this is just a second. Oh, this works now. Right. So it allows you to send in tuples, which will be read from left to right. Whichever condition hits first, that will be given as a result when you try to sub or put in a value there. So any questions on the piecewise thing? Okay. It's not working. Piecewise? Oh, oops. No, can you please repeat the question?
So you only defined it as described between 0 and 1.
Right. So Fourier series is generally computed for periodic functions. So when you see the Fourier series signature, the second argument is x 0 to 1. So I don't need the other definition, so I skip that. So the Fourier series will assume the function is periodic in an interval, and you give the periodic interval. Okay. Any questions on the series part? So further, you can try adding two formal power series or subtracting them. Try multiplication as well, see what happens. So as you can see that it will update the internal formula used for generating the series, so you don't have to recompute or do something like that, and you get the whole infinite expansion. Yes.
You define a piecewise function. How do you define
Like an interval, please.
less than something and greater than something?
So this is what I did, right? So okay, this piecewise takes in an x. If x is less than equal to is less than equal to half, it will return 1. Or if it is greater than equal to half, it will return -1. So this will be read left to right.
His question is like if you wanted to do x from 0 to 1.
X from 0 to 1/2. Okay. So maybe.
Try doing like and less than or equal to something and greater than something else.
Maybe we can define an interval.
So there's actually there's a few issues that if you try to do this, like you might just do it in Excel here. So one thing that you can't do is like this. You might want to do it like this. This is going to give you an error, and it's because the way Python evaluates this thing, there's like no way that SymPy can represent it symbolically. So what you really want is this, but again, this AND operator in Python is only going to work if it wants to give a Boolean value, and so that's what this error is telling you. It doesn't want to convert this thing into a Boolean because it wants to be symbolic. So what you instead should do is there's an AND function, or AND object rather. And I think the other way that you can do it is if you do x is contained in the interval from 0 to 1/2, and that'll give you the same thing as well.
So there's no special method in Python for and that is like for call or for greater than. There's a lot of built-in operators.
There
and
is.
there's a special magic method that you could override.
There is, like, that's how when you do x is less than or equal to rational 1/2, that's creating like that symbolic thing. So there is a special method, but the problem is there's no special method for like the chain operators.
No, but I was thinking for and that one could actually
Oh,
override.
no, not for and, not for like the word and. That's like that's because Python's evaluating that directly. And they don't want to add a special method because that would slow down. Because right now it's a very fast. It's just like always take the Boolean to this and then the Boolean to that. If there was a special method, we would have to do like a method lookup every time there was an and somewhere in the code, and it would slow down all Python code that uses and. There's also an and sign, the ampersand. You can use that as well. But the problem is I think the way that the order of operation works, you have to use parentheses. So you can do like 0 is less than or equal to x.
Yeah, that's the hyperkey. That's fine. The word.
Ampersand x is less than or equal to. Oh, sorry. So the question was, is there a way to there's no Python operator for the and, like the AND and the answer is no, there's not, because Python wants to keep that operator very fast, and if there were like a double underscore thing for it, it would require Python to do a method lookup every time. It would slow down Python code. But there is a ampersand operator that does let you override, and you can use that. You just have to, if you use ampersand, I believe you need to I believe the way the precedence works is you need to use parentheses with these things, because otherwise it'll try to do 0 less than or equal to x and x, which is probably not what you want. Oh, yeah. So the logic operators do have override, and SymPy implements all the logic operators, and, or, XOR, and then also not, which is the tilde operator.
So please open this notebook. We will try some basic operations that will make your life easier in SymPy. So try these exercises out and let us know if you have trouble. So try the next exercise, up arrow. In SymPy, you can also substitute functions with another functions, and or in short expressions with another expressions. So try this little exercise and try to rewrite the trigonometry terms. Other than a dictionary, subs can also take a list of tuples, say replace tan x with that works. Suppose we have a series expansion and we want just terms to a certain order. This can be done using the order as well, but we will try to do this using the subs method. So try this exercise, please. Right.
Is it a single pass substitution? Like, it looks like it's single pass. Like, I substitute one variable in terms of another, and then substitute that in terms of another. Like,
Right.
sin and the tan and cos, for instance, if I order it such that first write cot is equal to 1 over tan x, and then say tan x is equal to sin by cos, everything is
Okay.
converted to sin by cos. But if I write tan is sin by cos,
So it will move it. So the question is sub single pass, or if tan x is substituted by sin x and cos x, and then sin x is substituted with something else, so do we get something else or the same result, right? So we can try it out.
it does look to be a single pass. I'm
Right.
just curious if I'm making a mistake or if that's the.
Sub is single pass, right? So
It depends on, I think by default it is not, but if you do simultaneous equals true.
okay. So it is not single pass by default. Right. It will move from left to right in a list. So, but this might be interesting if it's a dictionary then. So, right.
Yeah, there's actually no way you can make it so if you use a dictionary,
Mhm.
then it will try to do the right.
Right. Right.
How do you substitute it if you didn't know about the argument was x? Let's say you want to replace all like
Okay. So what SymPy offers is, say you have an expression sin x plus cos y. So one convenience attribute is args. It will give you all the arguments to that expression. So you can move inside it, or we also have so this will give you all the symbols in the expression. So you get a list of all the symbols, or you can use the args for finding out what all it contains, right? Right, clear? Atoms are the smallest elements. matlab, They cannot be decomposed further. Next, a small image. So this is a small exercise on evalf. Just a quick Python refresher. You can split strings. Any more questions? Right. We can use the replace function as well. So just a quick. Oh, right. So this also works. Next up, Amit will be teaching you something about matrices. Thanks.
So I'll be talking about matrices, and after that, Aaron will be talking about code generation capabilities of SymPy, and then Ondrej will show you some real-life examples of using SymPy. So SymPy has a matrix module. So this is how we represent a matrix in SymPy with the nested lists. And you can use some standard methods defined on this. For example, finding the determinant is .det. Inverse. So it is a small exercise to find the inverse of a matrix. And you can use operators on the matrices. So matrices have their custom behavior defined for the operators. Yeah.
Do you know how you find the determinant? Is it like the recursive formula, or is it like some determinant?
So this one. I guess this should be different for sparse and dense matrices.
Is it as if you're doing it by hand? That's what I'm asking. Or is it, I mean, I never known that.
So I think there's a dense, okay.
Yeah, there's like some algorithms that's like sort of reductions.
Okay, there's some algorithms to do some reductions and make it faster than what we do by hand. So exactly what you expect here. So you can verify if the inverse is correct or not by multiplying it by the matrix itself, and you should get an identity matrix. So you need to simplify it to get the identity matrix. So find methods to compute eigenvectors and eigenvalues. So these are the eigenvalues of M. And of course, you can do that same for eigenvectors as well. And you can access separate individual elements of matrices as well through this. So for example, the element at the 0, 0 index, and element at the all rows 0th column, and first row all columns. And by the way, matrices are mutable here, so they change in place. So questions? Okay, let's move to the advanced matrices now. So we need to get this matrix from this one. So basically, this 1, 2, 3 is the 0th column, 0th row is deleted here. So what we can do is, and then we can insert at the first position. Yeah, of course, you need to return this. So what's wrong with this, Aaron? Sorry? This one. Oh, sorry. Yeah, this is what we expected. So we need to create this matrix, and we have 4 in the place of 1 in an identity matrix. So there's a function for that, for creating an identity matrix, that is I. It creates a matrix of, if you give the order here, it will create a 3 by 3 identity matrix, and we can multiply that by 4. So yeah. So in this matrix, we have 2 comma 3 ones as a diagonal and 1 as diagonal. So there's a function for creating matrix by diagonal. So what you can do is, yeah. So a small exercise for you. So this can also be seen as a diagonal matrix with the upper diagonal is this, and the lower diagonal as this. Yeah. So here is a nice exercise for you. So f is an analytic function. So by analytic, I mean which has a convergent power series expansion. And so this is the formula for power series. And you can do the same for matrices as well, substituting x with m. And further, if M is a diagonalizable matrix, you can write it as there must exist a matrix P such that P into D, and D is a diagonal matrix, and multiplied by P inverse gives the matrix itself. So and the task is to basically find that matrix. So the diagonal matrix can be written as like this, and this is the property of diagonal matrix. So the matrix with the function comes out to be this, the function of diagonal elements. So we'll do that function right now. So let's create some dummy data for that and verify that all these are diagonalizable. And this is how you access an element, which I told you in the previous notebook. compute at function, assume that m is square diagonalizable. So I'll give you a couple of minutes for this. So first we need to find the P and D, this P and D for the matrix M. Now we need to find this, the function of all the diagonal elements of D. All right. So we need to collect all the diagonals of D and apply that function to that. So, and then we can calculate this P into D and P inverse. So the second step would be this. So all the diagonals would be, and the function is given in the as a parameter here. So all the diagonals of matrix D would be I comma I for I in the range of the shape of the matrix. So now you can return that matrix M. So diagonalized version. Remember this diag function which we used in the previous notebook. So I'm unpacking the diags list. Then P inverse. And this should work. Yeah. So the last one is a food for thought. And we'll have the last 5-minute break, and then Aaron will come and talk about code generation. And after that, Ondrej will come on the real-life examples of SymPy.
If you downloaded the examples before last night, you may not have this one. I'm just going to do some really basic walkthrough on some of the code generation stuff. This should answer some of the questions about how to make SymPy evaluate things faster. So as we learned before, we can if we have this expression, this is this radius function, this time for hydrogen. This time, so if we use lambdify, this will create like a NumPy function based on this. Another function that you can import from SymPy utilities to AutoWrap is this ufuncify. And what this is going to do is compile a NumPy ufunc for this expression, I think using either C or Fortran. And so we can see here, these are both giving the same answers. And they both have pretty much the same the same API. You have first the variables and then the expression. And so we can plot them, and then we can see here the ufunc version, which has been compiled down. Yeah, so the ufunc version is faster than the NumPy version because it's been compiled down to a ufunc, which means that it should avoid some of the unboxing problems that you get with just straight NumPy. And so here's a little more complicated example with the derivative like we did before. And again, the ufunc version is more efficient. And so the way that this works is for any, so here's our expression. For any SymPy expression, there are these various code printers. So for example, if I want to convert this expression into a C code, I can use the C code function. Let me move that up. And that'll print out a C version of this expression, which can then be put into a C program. And the same thing for Fortran. And you can see here, this is the Fortran version of this function. And so what this ufuncify is doing is it's automatically generating Fortran code to create a ufunc and then compiling it. And if you want to know more about this, you should come to my talk on Thursday. But SymPy supports tons of languages for code generation: C, Fortran. What else? LLVM, Julia, Octave, MATLAB. What am I forgetting? Pretty much. JavaScript, yeah. It's very extensible. So if there's a language you want to generate code for, it's not that difficult to add support for it. And so this is a good way to use SymPy to basically do your math, and then once you've done that, you use the code generation to get very fast forms of those expressions, which you can evaluate or insert into your some other larger program that you're compiling.
Is there a certain subset of features that we have to restrict ourselves to so that it applies to very fast code?
Well, I mean, so yeah, each code generation function is going to basically have whatever functions it supports. And so, for example, if you have some function that isn't implemented in the C standard math library, it's not going to know how to code generate that. So you'd have to have like some implementation of it, for instance, like if you have some special function. And there are other things like some languages, it's more difficult to generate code for certain kinds of things. But we're trying to add support for as much as we can. Questions, anyone? Otherwise, Ondrej is going to show you. I'm not sure what Ondrej is going to show you. But after that, if there's any other topics that you guys want to know about, just let us know.
So I will show you some examples how SymPy or how people use SymPy for some applications. If you pull from the repository, I put in there a new notebook in the applications directory. It's this NPendulum control notebook, and I'll put some links up there. I'll show it on from this NBviewer website because it has it shows the pictures there. So in this case, it's an example how to use SymPy to derive equations of motion of this system. It's an N pendulum problem, so it has a moving cart. It moves to the left or to the right, and then it has N pendulums kind of chained one to the other. And so you have their lengths, masses, angles, and And the cart could move, imagine like on a railway, and you would like to know the equations of motion, and you would like to know how to solve this problem. So you let it evolve, you would like to know how it's going to move. So SymPy has a SymPy physics mechanics module, which allows you to deal with these kind of systems. The way it works is that you create dynamic variables, in this case positions or the angles and velocities and forces. Masses and lengths you just leave as SymPy symbols. And then it has these reference frames, mechanisms to kind of create any kind of system you want. In this case, we'll create a pendulum. You can see I'm looping over n, where n is the number of pendulums I have. And you can see I'm constructing, using those reference frames, I'm constructing the whole system. And then the equations of motions are of the form, it's a matrix times derivatives, and then on the right-hand side it's a vector, it's the force. So we let SymPy to do all the calculations. So you can see it can derive the equations of motions. This is the matrix. And for the pendulums, you can see it's actually pretty structured. It's not that difficult to derive by hand, but even in this case, it's nice to do it automatically. The forces are here, that's the right-hand side. And then we can try to solve it. So you can see, you've seen the lambdify. So we lambdify it first, and then we use then we create a function that creates the right-hand side for SciPy, and we use SciPy's ODE int to solve it. And then we can plot it. So in this case, the initial conditions are specified here. It's all the pendulums are vertical, and then the initial velocities are, each velocity is a little bit to the right, angular velocity, so that the pendulum kind of falls. So you can see from the graph, all the pendulums start, all the angles are the same, and it's kind of vertical, and then eventually it evolves and becomes chaotic, as expected. If you have, actually all these problems are chaotic. If you let them evolve, you can just see the positions are just kind of randomly swinging. You can do the same for velocities. So I would like to show you the animation so that you can kind of imagine what it's doing. I think it's here. So yeah, so you can see it just moves randomly. And you can see it moves the card as well, kind of randomly. So that's one thing. But then you would like to know, well, so is there a way to move the card so that it swings the pendulums, let's say, and keeps them on top? Or, let's say, moves the pendulums from one side to the other. So that's the next section. Let me skip this. So it's called a controller. So now instead of leaving the card on its own, you actually have some engine there, some motor, and you can move it. And the input to this problem is, you know the angles of each pendulum, and you know the velocities. And then you have to use this information as an input to the SciPy's integration routine, so that it tells you, you tell it where the card should be, and then you let it integrate using SciPy and see if it works. And it turns out this physical problem, you have to linearize it. So again, you use SymPy to linearize it and so on. I'll skip the details. I'll just show the result. So as you can see, again, we integrate using OD int. And here's the solution. I'll show the animation. So in this case, it starts vertical, and you can see it's moving to the other side and balancing it at each step. And this is done using SciPy's OD int, so there is no cheating. You just have to prescribe the forces, and you let OD int to numerically integrate the equations of motion. And if you go to YouTube, you can find a lot of videos. I put a link on the top. I'll just show you one. So this is a triple pendulum. and it starts at the bottom and it swings it into vertical position. And then it will swing it down in a few seconds in a controlled motion. That's also the difficult. You'll see now it's swinging it down and it stops almost immediately. Now it swings it back up. And now it will just let it go. So you'll see what it does when the controller doesn't do anything. It just lets the cart move. So it just, you see a similar motion as we've seen on the video previously. They even have they publish this, so you can download the publication and you can see the equations of motion here. So they do it by hand. It's only 3 pendulums, so in this case they can do it by hand. But it's nice to be able to do this automatically. So people use it when they want to simulate a bicycle, for example. Then the equations are very complicated. You cannot do it by hand, and a SymPy can do that. And the project that uses the SymPy mechanics is called PyDi, and there is a tutorial in the afternoon. Well, and let me show you another application. So I need it for a kind of numerical finite element simulation. I needed quadrature rules with high accuracy and high order. So SciPy has routines that can do that, but they use numerical algorithms to calculate these quadrature rules, Gaussian quadrature rules. And it turns out that for high order, they are not as accurate. And so I needed to have full double precision accuracy for all those weights and points. So in SymPy, you can use integrals.quadrature, and then let's say Gauss-Legendre quadrature. So you can just call it. You tell it which order you want and how many digits you want, and you can do more. You can do 30 digits if you want. And then I use that to essentially generate a Fortran code with those quadrature rules. So in this case, you might think, oh, this is a simple example, but when I needed it, SymPy could not do it, so I had to implement it. So it's interesting here how it's actually implemented and how you can implement similar kind of things. So you can, let's see if I can, I'll just copy it so that you can see it. Let's see, let's just put it here. So you can see it's using Legendre polynomial, which is just a symbolic polynomial, and then it calculates real roots symbolically. So if the polynomial is short, it can give you an answer, but if it's more than 3 or 4, it only gives you a symbolic answer using a class called root of. And then this root of class has a function called eval rational, which gives you a rational approximation of this root to an accuracy that you specify. And then I evaluate this approximation numerically, again, to as many digits as I specify. And then for weights, you just use a standard formula for calculating the weight. It involves knowing the derivative of the polynomials and so on. And so the point here is that you can set these n digits high, and then you get as many digits as you need accurately, all of them. So that's very, very useful to check that numerical routines, let's say in SciPy, so it's, for high order, don't give you all the 17 digits that you can get in double precision. And so this is kind of a way how you can implement your own equations, your own quadrature, if SymPy doesn't have it. And if you do, send us a pull request, please, so that we can have it in. And so we have about 10 minutes left, and so Aaron will answer, and we all will answer questions, or if you have anything you would like us to show you that we did not cover, or if you have any questions. I guess that's like... Well, if there are no questions, we'll be here feel free to talk to us during the conference.